Welcome. This is the AP Physics lecture on kinematics, the kinematics equation. This is the objective for the lesson. So we left off with looking at the acceleration equation. We saw that acceleration is equal to the delta v over delta t. We can expand it because delta means final minus initial. So a equals to v minus v naught divided by t minus t naught. What we can do is if we take t naught equals to 0, it simplifies into this equation here where a is equal to v minus v naught over t. Doing some algebra, if we multiply both sides by t, you get ta is equal to v minus v naught. Add v naught to both sides. You get left over v is equal to v naught plus at. They just rewrote it as v equals v naught plus at. This is the most simple of the kinematics equation. We can rewrite it like this. The reason why we rewrite it like this is because we should see that it behaves like y equals mx plus b, which is a linear equation. So this behaves very linearly, where the slope is equal to the acceleration and the y-intercept is the initial velocity. Expanding that equation, we could get our next kinematics equation. Then we can do other things to combine to make a third kinematics equation. All the different kinematics equations are used differently, but derived from the same point. You would never be asked to derive the kinematics equation on the AP Physics exam. You would just learn how to use them. There are several ways to solve for average velocity as well. These are the two ways. Vectors and kinematics equation. So the kinematics equations are vector components. Therefore, they can be broken up into your x component and your y component. This is how it looks like. The only difference is the subscript of x, which is on the variables, like so. You should notice that both are the same. What you would like to see is when to use it. Here I have some slides on how velocity and acceleration affects the motion. And you should go over this at your own time if you would like to see it. Pause the video if you would like to copy down any notes. Here's example 2. All what we're doing is rearranging acceleration as positive or negative and seeing how it affects the final answer. And this is the last one, example 3. And this is example 4. What you should pick up is when a object starts at rest, which is stationary, and act upon by an acceleration, the object can speed up and will move in the direction of the acceleration. When the direction of acceleration is actually the same as the direction of the initial velocity, the object can only speed up. And when the direction of the object is in the opposite direction of the initial velocity, the resulting velocity depends on how long the acceleration is. And here are some examples. You're going to see how it works like when we do some problems. But these are some notes if you would like to take a look. Now, we would like to look at why we have to include the x and y when writing the equation. The answer is technically no. In some problems, both the horizontal and vertical motions are the same. So you would have to write the subscript if it's talking about 2D. But when we're only talking about one path, you won't need to write it. And again, you're going to see it as you do more problems. Remember, the kinematics equations are limited to what type of motion? It's only constant acceleration type of motion. Remember, acceleration must be constant. Now, we can take a look at our 3 kinematics equation here. And here I just wrote it in the x direction. And this is when there's 3 different cases. This is the first one is the no final speed. This is when there is no basically v. You should see there's no v here. When there's no time, there's no t component, and when there's no position, there is no x. If you can rewrite this in terms of displacement, which is delta x is equal to x minus x naught, you should see that you can minus x naught here from both sides. That's how they get the delta x version. Same thing here. This simplifies into delta x. And the no position one stays the same because there's no position part to it. Then lastly, if the object starts at rest, we know that v naught equals to 0. We can simplify by this going to 0. That's how you got this value down here. Same thing on this side. This went to 0. Then to get v alone, use square root. That's how they got this part down here. And the last one, the v naught term just goes to 0. That's how they got this value. Those are all your different ways of rewriting it. Some students ask which one should they memorize. Please understand that these 3 equations are given on the formula sheet. This you have to derive. The rest you could also derive as well. So these are the main ones that you will find on the formula sheet. The rest you have to be able to derive. And lastly, this is when the object has constant velocity. So when constant velocity is when a equals to 0. This is a rare case, but I just wanted to show you this one as well. Let's look at the variable list. Each time when you solve the problem, you will notice that a lot of the physics problems are wordy, vague, and there's a lot of different things to occur on the problem. So the question is, how do you keep it straight? This is why we recommend you make a list of variables. The list of variables will change the complex problem into a simple math problem for you to be able to solve. This includes zeros, plus and minus signs. In short, the variable list makes it easier to select the right equation. It is going to be impossible for you to solve any physics problem without writing down the variables. When you read a physics problem, sometimes the wording of the question will hint certain variables. These are called the hidden variables. If your question says, starting at the origin, that means x naught is equal to 0. This also might include y naught equals to 0 as well. Initially at rest means v naught equals to 0. Comes to a complete stop means v equals to 0, which is final velocity. And if they say constant velocity, that means a is equal to 0 because there is no acceleration when there is constant velocity. What does each kinematics variable represent? If you see x naught, that means initial position. X means final position. If you get a positive value for those, that means the location is to the right of the origin. If it is negative, it means it is to the left of the origin. And if it's located right at the center, it is 0. If you see delta x, that means displacement. If it's positive, means the object is moving to the right. If it's negative, the object is to the left. And if it's 0, the object is stationary. V naught, which is the starting velocity or an initial velocity, same thing. Same thing for v, which stands for final velocity. A stands for acceleration. If it's positive, it means usually speeding up. Negative means usually slowing down. And if it's 0, that means constant velocity. T stands for the elapse of time. Notice that the reason why we use elapse of time is because delta t is equal to t minus t naught, and we always set t naught equals to 0. That is the reason why t is used as the elapse of time. and it is always positive in our case. We will never have negative or zero time. But that is possible in higher division physics. Some assumptions that we have to make when we solve these problems. Please notice that every single one of these problems are occurring on Earth unless the question states. Assume the simplest environment. Assume that the motion is horizontal unless incline or vertical motion is mentioned. Assume no friction or air resistance unless the problem states. If starting location and direction are not given, then you can set them. Select an initial position and direction of the motion that is mathematically easy for you. And this is what we have. This is the flow chart on how to solve a calculation problem in physics. Step 1 is to always draw a picture that helps you visualize the problem. Then after that, find what you're looking for. Look for the quality that you're looking for and put a question mark there. Next, extract all the variables that is the variable equation list. Make some assumptions about a variable if you need it. That refers to the hidden variables. Next, ask yourself, what equation do I have that allows me to solve for my unknown? If you have the correct equation, you can use that equation to solve for your unknown. Check the units and variables to see if that makes physical sense. If not, see if you can create an equation. If you can't create an equation, you might have missed a variable, or you might have to go back and look at if you made any bad assumptions at the start. This is the basic flowchart of any calculation problem. We're going to see how this works in our first example. Example 1. An object initially at rest accelerates uniformly at 6.0 meters per second while moving 250 meters. Determine the time for the motion. Step 1 is to set up a picture. Here I have paint. An object is at rest, so I put the dot. I put v not equals to 0. It says it travels positive in the positive direction at v is equal to 6.0. Oh, it says accelerate, so this should be a equals to 6.0 meters per second squared. While moving 250, that is this distance here. Or you don't even have to put distance, you could put delta x because that is its displacement of 250. And you are looking for time. This is a very good picture. This gives me a visualization of this dot moving, what direction and what the variables are. Ask yourself what you're looking for, and we know it is the t, so we put a question mark there. Then we list the variables of what we're trying to solve. Delta x equals to 50, v naught is equal to 0. That is one of the hidden words. We saw that from the phrase initially at rest. V, our final velocity, was never given, and a is equal to 6.0 meters per second squared because that was given in the problem. Once I write my variable list, I can decide on an equation. I go back to one of those equations that I had from before. Also, I can look at my variable list. I saw that delta x can be equal to this. Notice I do not include the subscript here. What I wrote here is what the equation normally is with the subscript x. The reason why I do not include the subscript of x is like what I said before. This is a one-dimensional object going in the x direction, so the subscript doesn't have to be written. Next, I can substitute then solve for the problem. This is my original equation. Make the substitution. So the 250 goes in for the delta x. The a goes in for 6.0. Simplify. That is me just doing the 1/2 times 6 becomes 3. Divide both sides by 3. I get t squared equals to 250 over 3. Remember, I don't round it. I keep it as a fraction until the end. The reason why is I have to square root both sides to get t alone. I get t equals to 9.3. That is me rounding the answer. This is if you want to substitute, then solve. I have another way of doing it. This is when you solve, then substitute. What I mean by solve is that I actually solve for the literal equation. So this is what you did from before. What I did here is I solved for t because that is what the question is asking for. Then I just have one step of substituting. Either way, you're still going to get to the final answer. It just depends if you want to move variables around, or like before, you want to move the numerical values around. Up to you. You're still doing the same thing mathematically. You should still get the same answer of 9.13 seconds for t. Example 2. An object moves at 3.2 meters per second, decelerates to a stop in a distance to 240 meters. Determine the object's acceleration. Again, you should draw a picture, do a list of variables. But here I decided to skip that for the sake of the video. This is my list of variables that I have. Based on the variables, I look at my equation list and I look for the one that doesn't actually have time. This is the only one that actually has no time component. Solving for the literal equation here, I can show this to you if you would like to have me do the algebra. So this is the initial equation. Then I'm going to subtract v squared naught from both sides. I get v squared minus v squared naught is equal to 2a delta x. Divide both sides by 2 delta x. 2 delta x, I get what I have, right? A is equal to v squared minus v squared naught minus divide by 2 delta x. That is just me going over this if you would like to see how I got to that literal equation for solving for A. Substitute, get the answer. Acceleration can be negative. It just shows that the object, this makes sense because the object is slowing down. Good. Next, example 3. An object with an initial velocity of 10 meters per second accelerates to a speed of 200 meters per second in the distance of 100 meters. Determine the time during this motion. So set up your equation, set up your picture, write your unknowns. This is what I have here. Now you want to decide on the equation after you have your after you list all your variables. But there's actually a problem here. Sometimes there are multiple unknowns that would make it impossible to a second equation. Remember, for there to be an equation to be solvable, one equation for one unknown. That is basically the rule of algebra. Here you can't solve for it because you need A and T. So acceleration and time are unknown. Therefore, two unknowns are in the problem. Therefore, we need two equations. I will first set up this equation to solve for the acceleration. Then once I have that, I can use my second equation to solve for the time. This is going to solve for time because I got the acceleration from above. The reason why we can't just jump to this equation from the first part is because you have both A and T missing. That is the reason why you need the first equation. Let's see how it works. Here are the list of variables again, and I remember my first equation was this. This has no time component to it, right? Solving for the literal equation, then making the substitution, I got A equals to 1.5 meters per second squared. Now I have my list of variables. Notice now I have an acceleration. I just need time. So I repeat this again, but now with the new equation, V equals to V naught plus AT. Solve for T, make the substitution. You got T equals to 6.67 seconds. Notice it is very simple. The hard part about this is making sure you understand that you have to set up two equations. Example 4. Sometimes you have one of these problems that asks us to determine how something changes. Okay? Again, you set up the same way. The fact that there's no variables, you can still use the variable list. Just put a check off. It says there's a uniform acceleration, so you can put down there's an acceleration. It's from at rest, so v naught equals to 0. It reaches the speed of v, that means you have a v here. and it moves a distance x, so therefore you could use delta x. Here you see that there's no time component. The only equation that you have without time is v squared equals to v naught squared plus 2a delta x. But you notice that you have your v naught equals to 0, so you can now get v equals to delta 2 over v equals the square root 2ax. How I got that is this. Let me show you the algebra really quick. This goes to 0. V squared is equal to 2a delta x divided by, now you want to square root both sides. You get v is equal to square root 2a delta x. Okay? That's how I got here. So, next, you would have to set up to see how the final equation happens if it's doubled. Again, I write my final equation. So this was my initial. If you remember from our problems at the week, this is my initial, and this was my final. Okay, and look at how things canceled. Okay, v's will cancel, v's will cancel. Square root the 2 over a will cancel, as well as the x. Here, same thing, right? So what are you left over here is the square root of 2. So we would say that doubling x increases the right hand side by a square root of 2, because what is left here is just a square root of 2. Okay, there you go. That's how they got it. So we saw that the left side also has to be multiplied by the square root of 2. Example 5. Sometimes you might have a situation like this. An object moves in the x direction at 25 meters per second. At the instant it passes through the origin, encountering an acceleration 3.0 meters per second squared, directly opposite to that. The acceleration ceases to act when the object is 6.0 meters to the right. Determine the elapsed time of the acceleration. So, this is the symbols. The reason why it's a negative 6.0 is because it's going in the opposite direction. It's to the left. It's to the left of the object. That is why. It's a positive 25 because it says in the x direction. We do not given a final velocity, but you know acceleration is negative because it says opposite the motion. And here it says determine the time. So that's the question mark. Now, to do this, you only have this equation. And notice that once you substitute it in and rearrange, it behaves like a quadratic equation. Ax squared plus bx plus c. There's only one way to solve this, is the quadratic equation. And the reason why, once the quadratic equation, there's two parts, a positive part and a negative part. You're only going to take the positive part because a negative time makes no sense. If you would like to, if you get to this point, what I recommend you do is just open up a calculator and just enter it in. A was negative 1.5, the B was 25, and the C was 6. Hit calculate. Here it tells you the values. X can either be 0.2 or X can be 16.9, which is just 17. That's how I got that answer there. Okay. Again, you should not need to know how to do it, but if you want to see how it's done, it's here. Okay. But you just need to make sure you can get the final value. That's why I just recommend you use the calculator for it here. But here, please understand that problems like this can become a quadratic equation. You could actually do this without the quadratic equation, but it requires two equations. Notice that our v here was unknown. So what they're going to do here is to solve for v first. Make the square root it to get an answer, and they get this. Notice that if the object is to the left of the origin, it must move left. It doesn't matter how you plug this in, you're going to just see how time is in the end. So here, we choose it to be the negative velocity, so we pick this one. Then we go back to our most simplest equation, which is v equals v naught plus at, because again, we have v naught. Do we have v naught? Do we have v naught? Yeah, we have v naught here, we have a, and we have t. Okay, that's why we can set up this equation. Rearrange, plug it in, we get t equals to 17. Please understand that problems can be solved using different methods more than once. Most likely, the biggest one is the quadratic equation. So this is something that I always tell students. If it's a quadratic, if you need time, you're either going to do it one of two ways. You're going to have to end up using the quadratic one, which is this bad boy. V naught t plus 1/2 a t squared. This, or you're going to have to, I recommend using both of v squared plus v squared naught plus this one, okay, which is solving for v, then using v naught plus at. Okay, so there's two ways of doing it: the quadratic way or this way, which means solving for v first, then using this one. Okay, so please understand that either way you do it, you're still going to get the same answer. So lastly, that's about it. Sometimes you are going to be given multiple steps, so make sure you can calculate it. Okay, all right, but there you go.